So we were trying to find the RMS value here. We said that RMS and effective, we use those terms simultaneously. We'll probably use more RMS. And we set up this function last time. I'd refer you to our work last time if you're having trouble setting it up. One thing we have to be careful of is we had to look at the full period. So even though we have this section of 0 in here, that was still included in the period. So the period of this is 3 rather than 2. And then I broke it up for the region from 0 to 1, from 1 to 2, and 2 to 3, and just came up with the equation of the line in there. The third one was, of course, the easiest. And we put together our function, because remember RMS is you square the function, you take the average of the function, and then you take the square root or the root of the function. And we come up with something like this. Probably the trickiest part in this problem is dealing with that term right there, because you're going to have to square it out. Maybe I'll do that right here. 2t minus 4, and I'm squaring that out. 2t minus 4, what's that going to give way to? 4t squared plus, is it plus? No, minus 16t. Is that right? 16t plus 16. Is that how you do that? I think so. What am I going to have? I'm going to have 2t times minus 4 will give me minus 8t, and then I do that again. Yeah, minus 16t. Those are positive. So we got to make sure we have it for that. A lot of people in a stressful situation like an exam or something will try and sell that off as 4t squared minus 16, which of course it is not. Well, if I go through then the integration, I'm going to have the RMS value is equal to the square root of a third times all kinds of brackets here. What are we going to have here? This will be 4t cubed divided by 3 evaluated at 0 and 1. Then we'll add to that. What are we going to have here? 4t cubed over 3 minus 16t squared divided by 2 plus 16. No, because I square the 2. Yeah. Okay, so this is from what, 1 to 2, and then I have 0 in there. So I'd better put the bracket on there like that. So from there on, it should be algebra, pretty straightforward. I'm not going to belabor that, although a lot of times people make mistakes in the algebra or just the arithmetic, so be careful with that. But you can check it on your own. You should come up with IRMS being equal to 0.94 amps. So what do you think about that for an answer? We agreed last time that it should be what? Did anyone check this at home? Yeah, good. You come up with the same answer?
Yeah, 2 red, 2 blue.
Great. Good. You kept it in radical, a real math guru there. So good. Okay, so we got confirmation from one. Anyone else? A second? Okay. Few people? Great. We agreed when we left last time that the answer should be between what? 0 and 2. Absolutely. It should be between 0 and 2. So if someone came up with 9.4, they'd lost a decimal place or something like that, we'd know that was wrong. If it was 3, we'd know that's wrong. It's got to be somewhere between 0 and 2, and that makes sense. And a third of the period is at 0, so we would expect it to be significantly lower than 2, because we're looking at a DC equivalent. Essentially, I don't want to commit heresy here, but essentially kind of a running average of this wave, right? Okay, and this piece here, being at 0 for a third of the period, is going to pull that down. Well, we're pretty well finished up with our RMS topic. I guess one thing maybe we should look at. This pen's about tired. So we said that for a sine wave or a cosine wave, what do we have? That our maximum value we'll talk voltage here, you could talk current or whatever you wanted. We take our maximum value and we divide it by the square root of 2 to get our RMS value. Is that right? Is that what we had? Okay. So when we talk about a, let's say 110 volts or 120 volts AC, that is really RMS. So when we look at the plug-in over there, at 110 or 120, that's RMS. So what's our peak value? And graphically what we have here is we thought we had a sine wave where the maximum was up here at 100, and let's take 120 just for easy figuring. So we thought this was up here at 120, and that's actually not true. What we have is we have the DC equivalent that's at 120, so this maximum value is up there quite a bit higher. So what we do, we take this 120, we'd multiply it by the square root of 2, and what do we come up with? $170 volts? Yeah, so we'd be up here at about 170. Okay. This is why when we first sat down to the oscilloscopes at the end of last term and you grabbed your digital voltmeter that you were used to and you started to put it on the circuit and compare it with what you were seeing in the oscilloscope, they didn't work out because most digital voltmeters are going to be measuring RMS. Okay? And your oscilloscope is measuring the wave itself, right? But now you know that if your oscilloscope comes back at 120 volts and it's a sine or cosine, you should be able to make that work out, make that coincide with what you see on the screen, right? Okay. Questions with that? Okay. So the next thing we're going to talk about is power factor. I always think that's an interesting title. Looks like maybe it should be some sort of a reality TV show or something like that. If you come up with a good idea on that, I get a few percent of that. So you got the power factor, and we learned as we got into power that the average power was equal to, I think we said the average power was equal to 1/2 Vm Im times the cosine of this angle of the voltage minus the angle of the current, right? Which happens to be the angle of the impedance. The difference between the current and the voltage angle is the angle of the impedance. If I write that slightly different, combine that half a little different, I think I have this expression right there. And that's for a sine, or for that matter, a cosine. That's how we developed that, based on the sine or the cosine wave. And then we said, well, if we want to make this a little more useful, we could talk about RMS. So we could say that we have then, using that square root of 2, really this turns out to be VRMS times IRMS times the cosine of theta minus phi. And this is really good for all waves. So if we're looking at a square wave, triangular wave, or something like that. Now, we want to try and break this up. I mean, we've got nothing new up to this point, right? But what I do want to do is I want to start to divvy these up with different names. I want to take this, the product of VRMS times IRMS, and I'm going to call that the apparent power. So I'm just starting to give things different names, slicing them up and calling them different things. So the product of VRMS times IRMS, I call the apparent power. And then, because I like to give things new names, I can call the power factor the ratio of the average power over the apparent power. Well, if you look at the ratio of the average power over the apparent power, that's what this is. Okay? So this is your power factor. Okay? So you could really say, if you wanted to, you could say that the average power is equal to the apparent power times the power factor. So average power is equal to apparent power times the power factor. Now this power factor, this is very interesting. I want to spend some time looking at this. The power factor is the cosine of the angle of the voltage. Let's make this real clear, so I'll say sub V, minus the angle of the current, phi, so I'll say sub I, which would also be equal to the cosine of, What's the difference between the angle of the voltage and the angle of the current? That's the impedance, isn't it? I could say theta sub z for the angle of the impedance. Because if you look at the impedance, I mean, you go back here to, carve out a little area here, you go back here to Ohm's law, where phasor voltage V is equal to phasor current I times the impedance Z, and we could say that Z is equal to V divided by I, right? Where this would then be the impedance Z would be equal to the magnitude of the voltage divided by the magnitude of the current at an angle of, how do I handle the angles? Theta, that's the angle of the voltage, minus phi, the angle of the current, right? So it should not surprise us that this is the theta sub z. Those of you who got through lab this week recognize that, right? That angle that showed up in your impedance triangle was the same angle that showed up in your phasor diagram, or should have been. Okay. So with that, if I have a RC circuit, so we've got resistors and capacitors, an RC circuit, you're going to have a theta sub z that's what? Somewhere between minus 90 and 0, right? If it's predominantly resistive, it'll be 0. If it's predominantly capacitive, it's pretty close to minus 90. Some of you in lab, hopefully you didn't walk out thinking you had new phenomena there at minus 93 degrees or something. That gave you a negative resistance, didn't it? Okay, before you turn that in for patent, you probably would recognize that that small negative resistance is due to error in your measurements. Okay, about the best we can do is get here to minus 90. Now, if we have a resistor and a inductor, what do we have? So we got a resistor, and we have then an inductor, RL. Our theta sub z is going to be what? Between about 0 and positive 90 degrees, right? Okay. And we talk about this in terms of, we can talk about this, and we would say that an RC circuit, that would be a leading power factor, whereas an RL circuit is a lagging power factor. Okay. So if someone describes a circuit to you with a leading power factor, they're saying, hey, it's predominantly resistive and capacitive. Does that mean there's no inductors? Not necessarily. It just means the capacitors outshine the inductors. It's predominantly capacitive. If they describe it with a lagging power factor, what are they telling you? Predominantly inductive, right? Where's a big source of inductors? Windings, motors. You ever hear about people that rewind motors, put the windings back in motors when you get them, when they burn out and things like that? Yeah, motors have a tremendous amount of inductance. So a lot of industries use a lot of motors, so it's probably more common to have a lagging power factor. Now, as we'll see in some examples, the power company would really like us to have a power factor of unity, not to be leading or lagging. We have all these motors then, we're always fighting, we're always trying to get from a lagging power factor closer to a leading power factor, or closer to a power factor of unity. Questions with that then?
Why do we want a leading power?
Well, we'll go through that with an example. We'll see that we get efficiencies in terms of reducing our line losses if we can get closer to a power factor of unity. So, I guess maybe we should talk about one case where we just have purely resistive. So your theta sub z in that case would be equal to 0, right? So your power factor is going to be equal to 1. Okay. Now what if you have something where you have that is purely capacitive? So it's just capacitive, or it's just inductive. Theta sub z is going to be what? Plus or minus 90 degrees, ideally. If it's purely capacitive or purely inductive, purely capacitive, negative 90, purely inductive, positive 90. What's cosine of plus or minus 90? Yeah, your power factor is equal to 0, isn't it? Okay. So now we can start to describe things instead of with the impedance, we can start to describe it with the power factor if we want to. Well, let's use this in an example and answer the question that comes up, why would we want to try and change or improve or correct the power factor? And we'll start out from a problem like this. I realize there's a lot of verbiage there. I'm posting these in PDF after the lecture, so you'll have access to them. If you don't want to write that all down, you could leave yourself some room in your notes and copy that down at your leisure. But I think there's some value in going from this story problem. I mean, it would be a lot easier for me just to put a list of highlights, bullet points over to the left-hand side. I'm an engineer. I'm a male. So that would satisfy me more than writing this thing out. Okay? But I think there is some real advantage to going through this and reading the poem, so to speak, if you will. We're told an industrial load consumes 100 kilowatts. What in the world is that? That's about 134 horsepower. So we could put that down here. Maybe I'll start to draw a picture of this thing. So we've got a load here. So this is our load. And it's 100 kilowatts, which is about, and this is just kind of an FYI number, 134 horsepower. That's just for you and I to think about. Now we're going to look at this as a single-phase model. We probably in an industrial setting would not be running a single-phase motor of 134 horsepower. Any motor over about 5 horsepower is very uncommon not to be three-phase. But we haven't studied three-phase yet, so we'll take this as a single-phase. And quite frankly, the concepts that we learn in single-phase can apply very easily to three-phase. So we got that 100 kilowatts. Do they have large motors, 134 horsepower? Is that a small motor as far as industry goes? I mean, over at Reedsport, where they used to have International Paper, they moved out years ago, but they used to have mechanical digesters over there. I think they were 15,000 horsepower apiece. Okay, so you can get big motors. 134 horsepower, that's probably, those of you who worked on the farms and whatnot, that's a good-sized irrigation pump, but they make irrigation pumps a lot bigger than that, too. Okay. So we're told then that load is at a 0.707 power factor. Lagging, 0.707 lagging power factor. And the 60 hertz line voltage at the load, so we have some line voltage at the load, is, this is 60 hertz. And it is 480 at 0, and that's volts RMS. So it's important whether we're talking maximum or RMS. So that's what we have there. So that's our load. We're told that the line resistance between the electric meter, so out here we have the power poles. We've got the wires on the power poles coming in to the electric meter. And from the electric meter then to our load. Okay. And we're told that the wires have a resistance, and I'll just lump the resistance up right there, of 0.1 ohms. Okay, if that's our electric meter, who pays for the losses in this? Obviously with the resistor, we have losses, don't we? We're going to have power coming off with that. Heat, probably. Hopefully not light. Okay. Who pays for that? We do. It spins the meter, right? Yeah, it spins the meter. We have to pay for that. So what we'd like to do is we'd like to find the power savings if the power factor is corrected, and that's a very common term, corrected. So we're always talking about power factor correction. We're always trying to get closer to unity. We try and shift it back to 0.94. And this is really this is about your minimum. The power company is not going to tolerate you. They're going to fine you for actually running such an extreme power factor. So it's our task to try and correct this power factor up to 0.94. Okay, so let's see if we can go through this. You got this scenario here? Okay, so I think what I'd like to do is I'm going to come over here and I'm going to look at the average power for the load is going to be equal to V RMS times I RMS times the power factor, right? Pretty straightforward. This is the voltage. Here's the current. So I can say then that the magnitude of this current, I RMS, is going to be equal to the power of the load divided by V RMS times the power factor. So if I start to put numbers in here, we have 100 kilowatts. So 100,000 watts divided by VRMS is 480. That's the magnitude. Okay, these are just magnitudes. You notice there's no phasor dot. That's not an omission. They're magnitudes. It's not a phasor. And then the power factor. What was our power factor? 0.707. That's where we're starting out. Eventually we're going to try and correct that or improve that. And this turns out to be equal to 294.67 amps. Okay, and you certainly would not need that 0.67, just round up to 295, but I'll keep those values so you don't think I'm trying to fool you here. But in a practical sense, we definitely want to round that number off. So how much power do we have to buy at the meter? Well, let's see. So is that working here? Okay, so the power that we have to buy would simply be equal to the 100 kilowatts. We got to have that, 100 kilowatts, plus the power that's going to be dissipated in that resistor. Well, I could say that the power dissipated in a resistor, couldn't I say that that was I RMS squared times the resistance? Yeah, we saw that last time. So let me say that that is 294.67 squared times the resistance, which is 0.1. Okay, now I have to be careful. I got kilowatts here. This is going to turn out in watts, so I'm going to divide this by 1,000 for the units, so that this whole thing turns out to be kilowatts. Okay, so this is units. So when you get done with that, what are you going to have? 108.7 kilowatts. So our line losses are costing us 8.7 kilowatts. And we're hoping to improve this. We're hoping by reducing the power factor, or correcting the power factor, getting it closer to unity, that I can reduce that. So let's say we are somehow able to wave a magic wand and change our power factor. Instead of 0.707, it goes to 0.94. Now, in actuality, we have to do something there. We'd have to add some capacitance. We'd maybe have to change some motors. If our motors are all relatively new, maybe we're better off just going out and buying capacitors, and we'll put some capacitor banks in there. If you look at where power comes into large industrial settings, sometimes there's these great big boxes up there. That's what those are. Those are capacitors, and they're trying to fix their power factor. If our motors are about worn out, maybe we want to sit down and say, hey, maybe we can buy motors with a different power factor. And that's, that's an economic decision. So let me do this again then. We'll go back to the equation that we had here. I'm going to use this one again. And I'll say that IRMS, so this is now for the new, is equal to the power divided by VRMS times the power factor. So I still have that 100,000. I'm going to divide by the 480. That didn't change at all. And then I have, instead of 0.707, I have 94? So when you go through that, you come up with 221.63 amps. And that's actually amps RMS. I probably should have written this more carefully as amps RMS. Significant reduction in the current. Still a lot of current. I mean, for 300 amps, you're going to have a wire that's the size of your thumb. but we've reduced it from 294 to 221. Okay. I know everyone's got a different size thumb, but bear with me on this, okay? About somewhere around there, okay? When we're in lab, sometimes people make mistakes in their lab and they try and tell me that they got 300 amps down the little wires that we use in lab. Is that going to happen? For a moment. Okay. For a moment. Okay, so we've got the current there, so I can go through this again. And I can say then that my power at my source is equal to this 100 kilowatts plus, then I'm going to have, instead of 294, I'm going to have 221.63 squared times 0.1. That's the resistance in the line. I haven't changed that. Haven't bought new wire or anything. That's still the same. I still have this 1,000 to deal with the units so that this turns out in kilowatts and not watts. And this number turns out to be 104.9 kilowatts. So we saved about 4 kilowatts, right? I mean, if we look at the power savings, if we look at the power saved, we're going to have 108.7 minus 104.9, which gives me 3.77 kilowatts. We'll see how much that is. Let's say that we're running 24/7 and we're at 6 cents per kilowatt hour. Okay, which is pretty cheap. So I'll take this 3.77 kilowatts, 24 hours per day, multiply it by 6 cents per kilowatt hour. To cancel that with that and that with that, I come up with pennies per day, and I can convert that. Of course, there's 100 cents and a dollar, and you end up then with $5.42 per day. You might say, well, that's not very much, but over a year that would add up. Also, we're looking at a big industry. This might be just a fraction. We're talking about, 100 kilowatts? I mean, there's industries that are running hundreds and thousands times that. And this begins to be a very serious number. It's always interesting. This is a very common calculation that electrical engineers will do if they go into power. This is something they oftentimes give you. You know, we got to do an improvement on this piece of equipment. What are our savings if we try this option A or this option B? And you'll do a calculation very similar to this. Questions with that? So by keeping the power factor close to unity, you can keep that current lower and actually get savings that way. No questions? Yes?
So, let's say that there was like a vacant house just sitting there with nothing running on it. There would be current going to the house that you'd lose just from those wires. So, like, you bill on that, like, let's say no one lived there for a month.
Okay, yeah, well, I shouldn't say yeah, because I think the answer to your question is no. But,
something has to be used.
Yeah, because let's look at this. If we put a switch in this and we open this up, okay, and we open that switch, there's no current through here. So our calculation right over here, where we take this current and we square it, that goes to 0, so there'd be no losses. Okay, so you're only going to get those line losses if you're actually running the load. So if you have a house that's sitting vacant and the power meter is turned on, but nothing's running in the house, there should be no power consumed. Now the power company, I think there's the monthly charge whether you use power or not. They're going to get you for that. But there shouldn't be any kilowatt hours consumed. Other questions?
Do you have any methods of, there was like a sham, I don't know about if it was a sham, but this guy, he made some stuff that would actually generate his own power. He has on like wind power generator and some solar stuff on his house, and he would actually just, quote unquote, he would, have his meter turn the other way, and the power company would send him money.
Yeah, that's not a sham. If you have solar energy on your house or wind energy, and you're producing more than you use, it goes the other way, and they'll pay you for it. Yeah.
Some areas, though, you're not allowed to live off the power companies did that in Florida. They lived off their own water and power, and the area, the county, forced her to go back on the river.
Yeah, it gets a little more complex. They don't pay you the same rate that you consume power. They don't pay you per power. That gets a little more complex. The scams or the shams that you've probably heard about is in the old days, people would turn their meter upside down. They'd take it out. I mean, that's just stealing power there. So it's not particularly complicated.
Have you done anything like that, or do you know of ways to? Not the sham one. I mean,
What is this, confession here? No, I mean, that's stealing power. Most of the time, people don't steal power because they want power for free. They want power without getting caught using all the power. So what are they doing? But yeah, they're bypassing the meter, not because they want free power so that grandma can bake cookies. They want free power. Why? Yeah, they want to grow without getting busted for growing. I mean, if you go through a neighborhood and you look at all the power consumption, and there's one house that looks like the rest, and it's using 10 times the electricity as a DEA agent, what are you probably going to think?
Like the base.
Yeah, grandma must like to bake. Okay. Okay. So, yeah. Okay. Yeah. Emphasis on bake there. So. Yeah, so that's oftentimes when people are stealing power, it's for that. It's not necessarily because they're trying to get free power. So, okay. Well, where we're going to go next time, we actually got to a pretty good stopping point. We'll pick this up next time, but we're going to talk about maximum power. And if I were to talk to someone, I'd say talk about maximum power. In context, we should probably talk about maximum average power. We went through this discussion with DC circuits, and we'll see some of those conclusions, but the complex portion is going to be kind of different. That will lead us to the topic of a complex conjugate. So this is where we'll start when we get together next time, going through this derivation and seeing the implications of it. Have a great weekend.